single slit diffraction. Now let us have a single slit. This is the single slit of width small a. The width of the slit is small a. Let us have L and N. We have a plane wave front coming from infinity and striking this aperture A. Now let the center of the aperture A be M, and then we have a screen. We have a screen at a distance capital D. The center of the screen is O. Let us consider a point P making an angle theta at the center M of the aperture. Now all wavelets from L to N will be reaching this point P. All wavelets will be reaching the point P. Okay. Then the path difference between the wavelets reaching P from L and from N is this. Let us draw a perpendicular from L over here. Let this point be Q. So the path difference between the wavelets reaching P from L to N is NQ. If this length is A, if this aperture size is A, if this angle is theta, this angle is also theta. So NQ is the path difference delta x, which is written as A sine theta. When theta is small, then sine theta is approximately equal to theta, or we say that the path difference is A theta. The path difference delta x is A theta. As from the triangle MPO, this theta is arc OP upon MO. That means if the position of P with respect to origin O is x, theta can be written as arc x upon radius D. So this A theta becomes A x upon capital D, which is the path difference. Okay. Now we have three things. The first thing is the central bright fringe. The central bright fringe. Now let us consider the aperture again. What we have is, we have an aperture ln of width small a, and this is our screen. The center of the screen is O. All the wavelets from L to N, let us have these two wavelets, they reach O with a zero path difference. Then these two wavelets also reach O with a zero path difference. These two wavelets also reach O with a zero path difference, so on and so forth. Therefore, all wavelets reaching O, reaching this O, have a zero path difference. At the central point on the screen, the angle theta is 0. That is, all parts of the slit contribute in phase. All are in phase, that is, their phase difference is 0. This gives a maxima or maximum intensity at O, which is called as the central bright fringe. Now, what we say, the second part is the secondary minima. Why we call this as minima and why we call this as secondary is, minima means dark or destructive interference. Secondary means that there is some light, it is not completely dark. There is some light, it is not completely dark. Now, this is the aperture A. Now what we say, let the path difference delta x equal to a theta be equal to lambda. This is the first equation. Now that means theta is equal to lambda by a. Now the aperture ln can be thought of as divided into two parts, Lm and Mn. The wavelet from L and N have a path difference of lambda. Here it can be seen. And the wavelets from L and M have a path difference of lambda by 2. The wavelets from M and N have a path difference of lambda by 2. Okay. Then these wavelets from this hash and this hash have a path difference of lambda by 2. This star and this star have a path difference of lambda by 2. That means all wavelets from L to M have a counter wavelet from M to N which cancel each other. So all these wavelets are cancelled by all these wavelets, and at theta equal to lambda by a we have first minima. First minima. Minima के लिए dash for dark and it is first, so theta 1 dash is lambda by a. As theta was arc x upon capital D, which is lambda by a, so x comes out to be d lambda by a. It is a dark fringe, and the first dark fringe, first means 1 and the dark means dash. So we have a first minima at d lambda by a, positive for above O and negative for below O. Okay. Now this was the first case. In the second case, let us imagine that we have a slit whose width is small a. This is L, this is N. Let the path difference delta x, which was a theta, be equal to 2 lambda. So the wavelets from L to N have a path difference of 2 lambda. Let us divide Ln into 4 parts. L, M, N, O is already there, P is there, Q is there, R and S. That means if it is divided into 4 equal parts, the path difference between this and this is lambda by 2, this and this is lambda by 2, this is lambda by 2 and lambda by 2. So all wavelets from L to R have a counter wavelet from R to M and they cancel each other. Similarly, all wavelets from M to S have a counter wavelet from S to N and they also cancel each other. So over here at theta is 2 lambda by a, we have second minima. We have second minima. And theta is arc upon radius, which is 2 lambda by a. So the position x for second minima is 2d lambda by a. 2 stands for second and dash stands for dark. Okay. Now let us consider a third case. Third case C. We have secondary maxima. Secondary maxima. Now what we consider is, let the path difference a theta be equal to 3 by 2 lambda. The aperture which we have Ln, which has a width small a. The path difference between L and N is 3 lambda by 2. Let us divide Ln in 3 equal parts. Ln and let this be PQR. So whole Ln is divided into 3 parts. This wavelet from L and M have a path difference of lambda by 2. From M and R have a path difference of lambda by 2. From R and N have a path difference of lambda by 2. So all wavelets from L to M are cancelled by the counter wavelets from M to R. Only the wavelets from R to N remain, which reach the point P. Okay, that means at theta is equal to 3 lambda by 2a, we have a maxima. If we have a maxima, we call it as a secondary maxima, because the width of Rn is only a by 3. This is full A. The width of Rn is only a by 3. So the intensity over here, intensity is proportional to amplitude ka square. So intensity is equal to or proportional to, is equal to a by 3 ka whole square, that is a square by 9. That is 1/9 of the central bright fringe. Therefore this maxima is called as secondary. Now as this theta is 3 lambda by 2a, this theta can be written as x by capital D is 3 lambda by 2a. This x is 3d lambda upon 2a. This is the first bright fringe. So we say that this is the first bright fringe is x1. Similarly, if we say that the path difference, which is a theta, let it be equal to 5 lambda by 2. Now we think that we divide Ln, which is the width a of the aperture. The waves from L to N have a path difference of 5 lambda by 2. Let us divide Ln into 5 equal parts. They have a path difference of lambda by 2 each, 5 times lambda by 2. All these cancel each other except the last one. Therefore the last one, whose width is a by 5, sends light to the point P, and the intensity at point P is proportional to a by 5 ka whole square, that is approximately equal to a square by 25, that is 1/25 of central bright fringe. Okay, now From here, the theta becomes 5 lambda by 2a. This is the second bright, so we write it as theta by 2, the angular position of second bright fringe. As theta is arc x by d, that is 5 lambda by 2a, so x becomes 5d lambda upon 2a. This is the position of second bright fringe. Second bright fringe. If we plot all these in our diagram, what we obtain is, see, what we have is over here. Now if we plot x versus intensity, we plot here what is intensity. The intensity comes out to be something like this. Okay, now the central bright fringe, this is the central bright fringe. If we plot x over here, so the x is 0 and the first dark was at d lambda by a on the upper side of O and minus d lambda by a on the lower side. So the width of the central maxima, which is denoted by W, is 2d lambda by a. The position of second dark is 2d lambda by a. Second dark is 2d lambda by a. Okay, now the position of first bright, secondary bright or secondary maxima is 3 by 2d lambda by a here, and over here minus 3 by 2d lambda by a. Okay, so the width of the secondary maxima is 2d lambda by a minus d lambda by a is d lambda by a here, and here it is again d lambda by a. What we observe is the width of all secondary maxima is d lambda by a here also and d lambda by a here also, but the width of the central maxima is 2d lambda by a. Now if we see the angular position, of the first minima here and the first minima here, this theta is lambda by d here and this theta here is also lambda by d. So the angular position of the central bright fringe is again 2 lambda by a.